All right, so yeah, if you know the distance at aphelion, distance at perihelion, you can solve this for A. You can plug A in here. Remember, these are constants. This is the mass of the sun, so that's all a constant. That tells you the period of that object. So remember these relationships. This helps you with certain problems. Okay? But we're going to talk about angular momentum. And what's the angular momentum of a point source? Remember, L is angular momentum. It's the mass times the velocity, or its regular linear momentum, times the radius times the sine of the angle between the radius vector and the velocity vector. So, what's that mean? Well, if I figure out the angular momentum at aphelion, remember the object's going around counterclockwise, the velocity vector here is this. So its velocity at aphelion is here, and the radius at aphelion is that distance. So L, or the angular momentum at aphelion, at this point right here, is going to be the mass times the VA times RA times the sine of the angle. In this case, what is the angle? That angle is exactly 90 degrees. So at aphelion, then LA is just equal to MVA RA. Sine of theta goes to 1, because it's 90 degrees. And what is it at perihelion? Well, at perihelion, this is at perihelion, this is the mass times the velocity at perihelion times the radius at perihelion. And at this case, its velocity is this way. Notice I made that longer than that one because Kepler's second law says it's going faster at perihelion than it is at aphelion. And then we're going to prove that why. Right here, this is times the sine of the angle. But remember, the angle here again is 90 degrees. So the angle of perihelion is mv perihelion r perihelion, and this goes to 1. Well, if angular momentum is conserved, which it is because there's no external torques acting on this, there's no other object acting on it as it orbits, then those two have to be equivalent. Or what we can say is that LA is equal to LP, or MVA-RA is equal to MVP-RP. Notice the masses cancel. And mathematically, we just proved what Kepler did with this second law. As RA gets bigger, this distance gets bigger, the velocity gets smaller, so that stays constant. As the radius gets smaller, then the velocity gets bigger, so that those stay the same. So if you know this, if you know 3 of these, you can get the 4th one. Usually you know the distances and one velocity, you want to figure out what the other velocity is. So that works out quite well. Now remember, this is critical, this only works at aphelion and perihelion. Why? Why does it only work at those points? Because it's only at those 2 points right there where the angle between the radius vector and the velocity is 90, so that the sine of the angle goes away. If you pick any other point, it will work, but then you'd have to know the angle. For example, if I have a point here, the planet's here, the velocity vector is this way, the radius vector is this way, I have to know what that angle is. And that's harder to figure out. Okay? But it works good if you use it at aphelion and perihelion points. Those are the only points that it works really well at. It also, when they're trying to change orbits of a satellite, and it's in an elliptical orbit, what you want to do is you always want to fire the rockets when it's at perihelion or aphelion, because it's easier to change the rocket's orbit at that point. At that point, if you're at perihelion or aphelion, if I'm here, close to the sun, and I give it more energy, because it's perpendicular, what it means is it's just going to go further away, but it's going to stay in the same orbit. If you do it at some point here, it's going to change the orbit, and it's going to go in a different orbit completely. Where if you do it at these points, you're just going to shift the size of it. If you want to get it closer, what you do is at aphelion, you actually fire your rockets backwards, you slow it down. Okay? Or you do it here, you slow it down. Because if you do it here, you're going to increase the eccentricity. But if you do it at perihelion, you slow it down, it's not going to go as far, and you keep slowing it down every time at perihelion, eventually you get it into a circular orbit. That's what they did with something like Cassini mission. It went out to Saturn and orbited Saturn for like 20 years. When it first came in, it had this huge elliptical orbit, but every time around they would slow it down, and eventually it went into a circular orbit just outside Saturn's rings. So they worked their way down to a circular orbit by slowing it down at the perihelion. Or in that case, it would have been a parasaturnian system because it's around Saturn. All right, if you got all that, then you have a pretty good idea of how to deal with gravity. Now it's just figuring out how to do the problem. So I'm going to do a few example problems that I'm going to put up, just like usual for the other chapters.